Welcome to week 2, lecture 10, optimal consumption bundle. In this lecture, we are going to obtain the optimal consumption bundle for different consumer preferences. Preferably, we are going to look at non-convex preferences and Leontief preferences. That is the fixed proportion preferences. Now, for non-convex preferences, they are non-differentiable. So here, we are not going to use calculus to obtain the optimal values. So all we need to do here is to set up a particular argument and then use that argument to obtain the optimal values. For non-convex preferences, the optimal consumption bundle of goods is not at the point where the indifference curve is tangential to the budget line. The consumer will always want to choose a bundle on one of the axes. The optimal consumption bundle is not an interior optimum, but a corner solution. So, for all non-convex preferences, we know that the indifference curves are concave. They are concave. So because of the concavity of the indifference curves, the optimal consumption bundle is not at a point where the indifference curve is tangential to the budget line. It is not like the case where we have Cobb-Douglas preferences, where we have a downward slope in indifference curve, and this indifference curve is tangential to the budget line. So the optimal consumption bundle for all non-convex preferences occur on either the x or the y axis, on either the x axis or the y axis. So as a matter of fact, the optimal solution occurs at a corner point. So it is referred to as a corner solution. So for all non-convex preferences, there is no interior optimum. There is no interior optimum. We have a corner solution for all non-convex preferences. That is a situation where the preferences of the consumer is concave and not convex to the origin. Now let's take a look at this diagram. Now we see the indifference curves are all non-convex. In other words, they are concave. The green lines, they are all concave. Now, if we look at all these indifference curves, we have indifference curve 0, indifference curve 1, 2, and 3. So we have 4 indifference curves here. Now, the red line is the budget constraint of the consumer. So we notice that at different points on the budget line, we have a point where the budget line crosses the indifference curve. And there is one point where the budget line is tangential to the indifference curve. But is this an optimal point? Certainly not. This is not an optimal point. Because if we look at this indifference curve, it is very close to the origin. And we know what are the assumptions of indifference curve or consumer preferences. We say more is better. So are we going to get more here, or is the consumer going to consume more of both goods at this point? Certainly not. So if it moves away from this point, point O, away from the origin, we notice that it's going to be on a higher indifference curve. It's going to be on a higher indifference curve. That is, as it moves upwards, it consumes more of both goods, both good X and good Y. So that is why point 0 here is not an equilibrium point. It is not an optimal point. So this is not a preferred bundle. Similarly, point B, C, and D are not preferred bundle because the slope of the budget line is not equal to the slope of the indifference curve at those particular points. So for all those 3 points, we notice that the indifference curve is not, the marginal rate of substitution is not equal to the relative prices. So that is why B, C, and D are not preferable to the consumer. So because they are not preferable to the consumer, we say they are non-optimal points. Now let's look at point A. Point A is a preferred bundle, provided the price of good X is greater than the price of good Y. So it is a preferred bundle provided the price of good X is greater than the price of good Y. So if the price of good X is greater than the price of good Y, then A there is going to be a preferred bundle. So in many situations, in many instances, that could be the optimal solution to the consumer's problem. But let's look at point E. At point E, the price of good X is less than the price of good Y. So that is a preferred bundle if provided the price of good X is less than the price of good Y. So if the price of good X is less than the price of good Y, then the consumer is going to spend all his income on good X. So he's going to buy all of X and none of Y. And that is analogous or synonymous to M over Px. At point E, we say that is the intercept on the horizontal axis, which is M over Px. That is the income divided by the price of the good. At point A, that is the real income of the consumer. That is the income divided by the price of good Y. That is M over Py. So if A is the optimal point or optimal solution to the consumer's problem, then we say the price of good X is greater than the price of good Y. The consumer can easily substitute between good Y and good X. So is better off buying good Y because the price is lower than good X. So that is why he's going to spend all his income on good Y and none of X, if the price of good X is higher than the price of good Y. You need to note this one. This is very, very important. As a rational consumer, you always buy goods for which the price is lower. Now, if the price of, let's say, a particular drink, let's say Pepsi, it's like $2, or let's say 50 cents. And then Coke is like $1. As a rational consumer, you may tend to substitute Coke for Pepsi. So you're going to buy Pepsi instead of Coke. So in that particular case, all your income will be spent on Pepsi because the price is lower. So that is a simple case here. So if the price of one of good Y is lower than the price of good X, then the consumer is going to spend all his income on good Y. So it's going to be at point A. But if the price of good X is lower, the price of good X is lower than the price of good Y, then the consumer is going to spend all his income on good X, and it's going to be at point E. So as a matter of fact here, there is no interior solution. In other words, we don't have any interior optima in this case. So the solution to the consumer's problem is at a corner point. And so we have a corner solution. So the bundles of goods that are preferred are bundle A and bundle F. Bundle B, C, O, and D are not preferable to the consumer. Even though the indifference curve is tangential to the budget line at point O, it is not preferable to the consumer. Because at that particular point, the consumer is on a lower indifference curve, a curve that is very close to the origin. Now, let's look at one exercise here. Suppose the utility function of Bob is given as u of xy equals max xy, where max xy is the non-convex utility function of Bob. X is the amount of good X consumed, and Y is the amount of good Y consumed. Suppose a unit of good X cost $1 and that of good Y cost $2. What is the optimal consumption bundle of Bob if his weekly income is $10? Now, you see, for all non-convex preferences, the utility function is represented as what? U of xy equals max xy. So that is to say, for the two commodities, the consumer is going to look at the maximum, the good that gives him the greatest amount of satisfaction, the greatest utility. So all max function are function of what? Greater utility. So here the consumer is going to look at the commodity that is going to give him the greatest amount of satisfaction. And that is the commodity this consumer is going to spend all his income on. If, let's say, for example, the marginal utility derived from good Y is lower than the marginal utility derived from good X. So if the utility derived from Y is greater than the utility derived from X, then the consumer is going to spend all his income on good Y, because the marginal utility there is higher. So that's why we have this max here, the max. For all these utility functions, I don't know whether you have come across this one, but these functions are concave to the origin. They are not convex like the original indifference curve. They are concave to the origin. In other words, they are non-convex to the origin. So now we have the price of good 1, which is $1, and then the price of good 2, which is $2. A good Y, which is $2. What is the optimal consumption bundle of Bob in his weekly, if his weekly income is $10? So what you need to do here is you first of all set up the consumer's problem. Whenever you are faced with a problem like this, I'm going to repeat. Whenever you are faced with a problem like this, the first thing you need to do is to set up the consumer's problem. And the consumer's problem comprises of two equations. One, the objective function, that is what the consumer is going to maximize, what is his goal. Is it going to maximize output? Is it going to maximize cost? Is it going to minimize expenditure? Is it going to maximize utility? So that is going to be the objective function. That will be the first equation. And then the second equation is the budget constraint. That is the income. That's the income that the consumer has. So what is limited to? So that is what you're going to represent in the second equation, which is the budget constraint. And remember, the budget constraint is just like an expenditure equation. It consists of what? The expenditure on all the goods. If the consumer is maybe making a choice between two goods, X and Y, then it's going to be the expenditure on good X, which is X multiplied by PX. Remember, X is the amount or is the quantity of good X consumed. And then the PX is the price of good X. So you have to multiply that price by the quantity, and then you add the result to what? The expenditure on good Y, which is YPY. So the sum of those two expenditures gives the monthly or weekly income of the consumer. So here we are assuming that the consumer is going to spend his entire wealth on the goods. So that is the basic assumption here, that he's going to spend his entire wealth on the goods. So there is nothing like savings here. So if we proceed with this solution, we notice that the solution to this particular problem is similar to the solution for all perfect substitute preferences. Remember, we did the perfect substitute preferences where we have a consumer consuming two close substitutes for one another, like for example, maximizing u of x1, u of xy equals to x plus maybe 2y or 2x plus y, something like that. So that's a perfect. That is a perfect substitute preference. So the indifference curve there is a straight line. So we are going to use the same approach here to do the same problem. So these two are almost the same. We use the same approach to solve them. And the good thing is, here, we are not going to use any derivative or any calculus. So we are going to look at the utility function as well as the budget constraint, and then use them to solve the problem. So the first thing we need to do here is to set up the consumer's optimization problem. And what is the consumer's optimization problem? It is max xy, that is maximize xy, which is max of xy, subject to xpx plus ypy equals to m. Remember, m is the income of the consumer. Now, but since the price of good X is $1, price of good Y is $2, and the income is $10, then the budget constraint becomes what? X. Now remember, we don't say 1x here because the price of good X is 1. So it's just 1 times which is X. So it's X plus 2Y equals to 10. This implies that Y equals to 10 over 2 minus X over 2, or 5 minus 0.5x. Remember, you want to find Y here. You just take X to the other side of the equation. We transpose x, and then it becomes what? 2y equals to 10 minus x. Remember, whenever you transpose a variable, the sign in front of the variable changes. It changes. Now, this is for coding. Coding, when you change the place of a variable, or when you transpose a variable, you are changing the place of the variable. The variable is no longer on the left side, it's now on the right side. So the sign in front of it is going to change. So you have 2y equals to 10 minus x. So what we do now is what? We divide both sides by the coefficient of y, the number in front of the variable. So the coefficient of y here is 2. So if we divide both sides by 2, 2y over 2 cancel. We have y equals to 10 over 2. 10 over 2, of course, is 5. And then we have x over 2. X over 2 is just the same as 1 over 2 times x. And 1 over 2 is 0.5. So it's minus 0.5x, right? So I'm doing this one because I need to get the intercept term for the budget constraint. Now, clearly, if we look at this value 5 here is this value 5 is the intercept on the vertical axis. And remember, this minus 0.5 is just the relative price of the two goods, which is px over py, right? Px is 1 and then py is just 2. So 1 over 2 is 0.5. So this is the relative price of the two goods, right? Now we want to find the intercept on the vertical axis. We want to find the intercept on the vertical axis. So how do we go about doing that? Now, when we look at this, we say x, we are going to make x the subject here of the equation. So what we do, we transpose 2y. When we transpose 2y, the sign in front of 2y changes to minus. And so we have x equals to 10 minus 2y, right? So once we have 10 minus 2y, x equals to 10 minus 2y, what we need to do here is to we now have y equals to 10 minus 2y, right? So 10 there is 10 over 1, which is m over px. Px is 1. 10 over 1 is just 10. And so this 10 is the intercept on the horizontal axis. The intercept, right? So this is the intercept on the horizontal axis, okay? The intercepts on the horizontal axis. So intercept on the horizontal axis, okay? So we have that. Then this 2 is the same as 2 over 1, which is the price of good y over the price of good x. So that is the relative prices. In other words, it's the slope of the budget line. So now we have our m over px there, which is 10, and then m over py, which is 5. Then we have our py over px, which is 2 over 1, which is 2. And then px over py is 1 over 2, which is 0.5. Right? So we're going to use these values to construct our budget constraint for this consumer. Now, if we do that, we have the utility function here, which is the max function. You see, it is clearly non-convex. Now, on the horizontal axis, we have m over px here, which is 10, right? And then we have m over py here, which is 5. So This blue point here is the optimal bundle. Now, the price of good X is $1. The price of good Y is $2. Now, because the price of good X is less than the price of good Y, the consumer is going to spend all his $10 on good Y, on good X. He's going to spend all his $10 on good X. So the optimal bundle here will be what? 10 units of X and 0 of Y. That is none of Y and then 10 of X. So he consumed all his income. He spent all his income on good X and none on good Y. So the optimal bundle is just 10, 0. The optimal bundle here is not 5, 0. He's not going to spend his income on good Y. Why? Because good Y is more expensive than good X. He's going to spend all his income on good X because it is relatively cheaper. Now, for the utility function y, u equals to x, y equals to max, utility function, Bob consumes the goods with the highest utility. This is why we have the word max outside the bracket of the utility function. Its preferences are non-convex, as we presented in the previous slide. The choice made by Bob between the two goods depends on the prices of the two goods. Now, if the price of good X is less than the price of good Y, Bob is going to spend all his income on good X. And so the optimal consumption bundle will be M over Px, which is 10, then Y star, which is 0. This means that Bob consumes none of good Y. So that is one optimal scenario. Now, the next scenario, if the price of good X is greater than the price of good Y, then it means good X becomes relatively more expensive and good Y cheaper. So he's going to spend all his income on good Y. And so in that case, we have M over Py, which is 5, and then 0 otherwise. So 0 for X. Okay? So this happens, let's say, if the price of good X were like $5, and then the price of good Y is $10. So he's going to spend everything on good Y. If the price of good X is the same as the price of good Y, then the consumer is indifferent between the two goods. He can either buy 0 of good X and 5 of good Y, or and 5 of good Y, or he will buy 10 of good X and 0 units of good Y. Right? So as a matter of fact, the optimal consumption bundle will be X star Y star, which is M over Px, which is equal to 10 if Px is less than Py. 0 otherwise. It is also equals to M over Py if Px is greater than Py. And then 0 otherwise. So therefore, Bob's consumption bundle is X star Y star, which is equals to 10, 0. So this is what Bob is going to do. He's going to spend all his $10 on good X. Why? Because good X is relatively cheaper than good Y. So he's going to spend all his income on good X. So that is the solution. There is no differentiation here. We don't have to differentiate nothing for these functions. Nothing. We don't differentiate anything here. Okay? So this is so simple to do. You look at the price of the goods. If the price of good one is smaller than the price of good there 2, then the optimal bundle will be what? All of good 1, and then none of good 2. Simple. If the price of good 2 is smaller than the price of good 1, then the consumer is going to buy everything, all of good 2 and none of good 1, right? So in that case, it's going to be M over P2. Got it? Now let's move on to other preferences, the Leontief preferences, optimal consumption bundle from Leontief preferences. Now we say Leontief preferences are fixed proportion indifference curves. That is to say, the consumer spend a fixed amount on the two commodities, and he cannot buy one without the other. Say, for example, you have shoes, you have left shoes and right shoes. You are better off having 2 pairs of shoes. That is to say, you are better off having equal amount of those 2 goods. Have equal amount of left as well as right shoes. You are not better off having more of one of the good, having more of left shoes and less of right shoes. So that is why for all Leontief preferences or fixed proportion preferences, the optimal allocation, the optimal consumption bundle is always at the kink of the indifference curve. It is always at the kink of the indifference curve. So, if the consumer has more of one of the variable, one of the goods, if he has more of one good, he is not better off having less of the other. So it's better off if he has the same amount of the 2 goods. If he has so as a matter of fact, the optimal bundle here is obtained by increasing the amount by an equal value. So the optimal solution must be at the kink of the indifference curve. So if we look at the diagram here, the L-shaped indifference curve, we notice that U0 is the lowest indifference curve. U1 is a little bit higher than U0, and then U2 is the highest indifference curve. So that is the most preferred indifference curve for this particular consumer, because that indifference curve is higher than all the other 2 indifference curves. So now let's look at the budget line. The budget line is tangential to that point at the kink of that L-shaped indifference curve. In other words, at the corner of that L-shaped indifference curve. So at that point, we have the optimal consumption bundle for each of the goods. Now notice that the marginal rate of substitution of good X for Y is infinity when we are moving up the vertical curve. And then when we are moving horizontally, the marginal rate of substitution is just 0. Right? So as you can see here, the U of XY is just the mean of AX, BY. Right? So it looks at what? The least amount of these two. Right? So that's why we have the mean here. That's why they call it mean. Okay. Now, let's consider the following Leontief utility function of a consumer. E of xy equals mean xy x2y, where x is the amount of good x and y is the amount of good y. Suppose the price per unit of good x is $2 and the price per unit of good y is $3. What is the optimal choice of the two goods if the monthly income is $600? Now let's look at this. Let's have a look at this. For this type of consumer utility, consumer preference, oh, I think I left the preferences there, right? Utility is maximized when the quantity, so you just add preferences there. For this type of consumer preferences, right? So it's not consumer utilities. Consumer preferences, utility is maximized when the quantity of both goods increases. So the only way you can maximize utility if the quantity of both goods increases. Now let's take, for example, you have left shoes and the right shoes. The only way you are going to maximize utility is for both the left as well as the right shoes increase by an equal amount. If one of them increases and then the other remains the same, you are not better off. You are not going to maximize your utility. So this is the reason why the optimal point occurs at the kink of the indifference curve. Because if you increase, you start at a particular kink. So from a particular kink, if you increase the amount of one good, whilst the other good remains the same, the consumer is not better off. Because the increased amount of the other good is worthless to the consumer because he cannot use that. He cannot derive maximum satisfaction from that particular increment. So it is useless for that good to for that increase to occur. So even if the number of left shoes increases to 1 million, and then maybe originally you have like two pairs of shoes, that is 2 pairs of left as well as right shoes, right? And somebody came and gave you like 1 million left shoes. Are you better off or worse off? You are not better off because you are not going to use those 1 million left shoes all by themselves. You cannot use them. So it means they are worthless. So the only way you can maximize your utility or satisfaction is by having an increased amount of the two goods by the same value. That is the only time when you experience an increase in welfare. Is when the quantity of those two goods, that is left shoes and right shoes, if they increase by the same amount, then you are going to maximize utility welfare. So that is why the point of optimality, or the point where the consumer maximizes satisfaction, occurs at the kink of the indifference curve. So if we start at one particular indifference curve and then say we increase the number of the amount of one of the good, that does not increase the welfare of the consumer. It does not increase its utility. So its utility will only be increased if the same quantity of good Y is able to be produced or made available to the consumer to match with the increase in X. So that's why I say here, having more of good X does not increase the welfare or rather the utility of the consumer, unless he has the same quantity of good Y to match the amount of good X. That is the only time when the consumer maximizes utility. So this is the reason why the point of optimality occurs at the kink of the indifference curve. So at that particular kink, the budget line is tangential to the indifference curve, the L-shaped indifference curve. That point of tangency represents the optimal consumption bundle for the two groups. So let's try to solve this problem. The utility maximization problem for this consumer is what? Maximize utility of xy equals to the mean of x and then 2y, subject to xpx plus ypy equals to m. Now, since the price of good x is $2 and then the price of good y is $3 and m is $600, the consumer's problem becomes maximize mean x, 2y, subject to 2x plus 3y equals to 600. So 2x plus 3y equals to 600 is the budget constraint of the consumer. With these Leontief preferences, the optimal consumption bundle satisfies the condition. Now remember that 45-degree line that crosses all those L shapes. That 45-degree line represents the optimal bundle. It shows where the optimal bundle is located. So the optimal consumption bundle satisfies that particular condition. And that particular condition is right on top of the 45-degree line. Because that 45-degree line cuts all the L-shaped indifference curve at the kink of the indifference curve. And one of those kinks is tangential to the budget line. And that represents the optimal consumption bundle of the consumer. So the solution to the consumer's problem is the intersection of the line, which is y equals to 2y, x equals to 2y with the budget line. The intersection of the line, the 45-degree line with the budget line. Since 2x plus 3y equals to 600 is the budget constraint, now substituting for x equals to 2y into this equation and solving gives the value of good y consumed. We substitute for x into the budget constraint by plugging for x equals to 2y. Now you see, x is equals to 2y. All you have to do here, just take this x, plug it into the budget constraint, which is what? 2x plus 3y equals to 600, right? Now instead of having x there, you just plug 2y there. So we no longer have x there, but what? 2y, right? So we are multiplying what? 2 by 2y plus 3y equals to 600. So what is 2 times 2 is 4, and then plus 3, that is 7. So 7y equals to 600. So the value of y is what? 600 by 7, which is what? 85.7. So this is the optimal bundle that this consumer is going to buy. That is the optimal bundle that is going to buy. Is this an interior optimum? Yes, it is. Because it's what? It is a positive amount of the good, right? It is an interior optimum. So the Leontief preferences, for all the Leontief preferences, the optimal consumption bundle occur at the interior optimum. The optimum consumption bundle is an interior optimum. It is not a corner solution. We only have a corner solution for what? Perfect substitutes, quasi-linear utility function, and then what? Non-convex preferences. These are the three that gives us what? Corner solutions. These are the three that gives us corner solutions. For all the other consumer preferences, or the other indifference scores, we have interior optimum as the solution to the consumer's maximization problem. So since x equals to 2y, it follows that x star will be equals to what? 2 times y star. And y star is 85.7. We multiply 85.7 by 2, that gives us 171.4. So now we have the optimal unit of x consumed, and then the optimal unit of y consumed as what? X is 171.4 and y is what? 85.7. So that is the solution to this consumer's problem. So the optimal choice of this consumer is therefore 171.4 and then 85.7. Oh, this was a mistake. So this 171.4 should come before the 85.7, right? So remember, this is the y star. That is the y star, right? And then this is what? The x star. That is the x star, okay? So all you need to do is to interchange this one. Where you see this y star, just put the x there, this 171.4, and then put this on the other side. So xy should be 171.4 and then 85.7. So if we represent this one here, we're going to have what? So we have good x here is what? 171.4, and then good y is 85.7. So this whole region represents the optimal consumption bundle of the consumer. Now, as you can see here, if we are at this particular point, at this kink, and then the consumer gets increased amount of good y, let's say up to this point, right? Let's say it gets increased amount of good y up to this point, right? Is that beneficial to the consumer? Certainly not. It is not beneficial to the consumer. it does not increase its utility. Its utility will only be increased if it gets increased amount of y as well as increased amount of x. And it has to be in the same quantity. If it gets the same increase in y as well as x, then the consumer is going to maximize its utility. But having one of the good does not do him any good. It is worthless. It is just like, for example, you have 2 pairs of shoes, and somebody came and gave you like 1 million left shoes. So are you going to be using 1 million left shoes? No, you're not going to be using 1 million left shoes. Certainly not. You're not going to be using that. So it is what? It is worthless. So so those 1 million left shoes will only be beneficial to you if they decide to give you another 1 million right shoes. So if you have 1 more million right shoes to go with the 1 million left shoes, then you are better off. Then hey, make a party, right? You're better off. Now you see the ray, the 45-degree line. The 45-degree line represents the fixed proportion of the two goods consumed. Now we say x equals to 2y. So the consumer gets what? Twice as much goods. X is 2 times that of y. It consumes what? It consumes 2 commodities, X and Y, right? But it consumes twice as many Y as X, right? So the amount of X's that it consumes is 2 times the amount of Y consumed. So you have to represent that condition on this 45-degree line. So it is that condition that you are going to substitute into the budget constraint to obtain the optimal consumption bundle. So it is fair enough here that we are not going to differentiate anything. We are not going to use the concept of derivatives here. All we have to do here is to look at the proportion of the two goods used by this consumer, and then we use that proportion to substitute to the budget constraint to obtain the optimal values. Now let's move on to the optimal consumption bundle from a Cobb-Douglas utility function. Now remember, we did this Cobb-Douglas utility function, and I noticed that most of you have some problems with this. Most of you have some problems with. I think this one is so easy and straightforward, because if you want to find the marginal utility of a good here, you are going to take the partial derivative of the utility function with respect to that particular good. But remember, you are holding the other good constant. You understand? You are holding it constant. So this is for Aminatu Adebayi. Aminatu Adebayi and Cody. Now, when you are differentiating, when you want to find the marginal utility here with respect to x1, right? You are going to hold x2 constant. Remember, this x2 does not change. So you need to add it to the marginal utility. It needs to appear in the marginal utility function. Okay? So let's say you want to differentiate this utility function with respect to x1. That is the u, the x1, right? So you are going to multiply this entire equation by 0.4. But remember, you are taking 1 from the power, right? So it is 0.4 times x1 to the power 0.4 minus 1. Remember, 0.4 minus 1 is just what? Negative 0.6, right? Okay. But remember, do we have to drop x2? No. We need to add that one to the marginal utility of good x1. So this x2 raised to the power 0.6 remains the same. You just bring it down. So you have 0.4 x1 to the minus 0.6, and then you bring the x2 to the power 0.6. So that's it. So once you do that, you get your marginal utility. You do the same thing for the marginal utility of good x2. If you are differentiating with respect to x2, you have to take the power of x2 here, the exponent of x2, and then you multiply by the entire utility equation. So it becomes 0.6 x1 to the 0.4. This time, this power remains unchanged, and then x2 to the 0.6 minus 1. So 0.6 minus 1 becomes it becomes negative 0.4. So did you see now what happens here? So when you are differentiating the utility function with respect to x2, now we did nothing to x1. We just dropped x1 down, x1 to the power 0.4. That one remains unchanged. What changes is what? The second variable. Similarly, if you are differentiating with respect to x1, it is only the first variable that changes. The second one remains unchanged. Okay? That's why we say you differentiate the function with respect to one variable, and then you hold the other variable constant. Okay? Now, let's go ahead and set up the consumer's optimizing problem. Now, to solve this problem, we start by setting up the consumer's problem as what? Maximize utility u of x1, x2 equals to x1 to the 0.4, x2 to the 0.6. Subject to what? x1 plus 4x2 equals to 100. Now, I am going to apply the easy method here. Now, I know most of you have some problems differentiating, but let us use a simple method here. You don't even need to go to Cambridge University to learn these things. You don't need to go to Harvard to learn these things. Now, let us first of all find the marginal utilities. Why do we need the marginal utilities, for God's sake? We need the marginal utilities because we want to find the marginal utility per dollar spent on each good. So according to the equimarginal principle, the consumer is in equilibrium if the marginal utility per dollar spent on each good is equal. That is to say, if the marginal utility per dollar spent on good 1 is the same as the marginal utility per dollar spent on good 2. So if that happens, then the consumer is in equilibrium. So that is the essence of doing all these ones. Because if we don't know the marginal utilities here, there is no way we're going to obtain the optimal point of the optimal solution for this consumer. So this is very, very important. Now, back to basics. Let's go back to basics, right? So now look at this utility function. Now try to maximize this one. Try to differentiate that utility function with respect to x1. You are going to differentiate this with respect to x1. And then you do the same thing with respect to x2. But remember, when you are differentiating this utility function with respect to x1, you are holding the other variable, which is x2 constant. That variable remains unchanged. So, the marginal utility of good 1 here is what? is 0.4 x1 to the minus 0.6 x2 to the 0.6. Now, what do you notice here? What do you observe in this case? You notice here that what I did here, I just multiply. I take the exponent of, I just take this exponent, the exponent of x1, and then I multiply the whole thing by 0.4. That is x1 to the power 0.4, x2 to the 0.6 by 0.4. But remember, we always need to subtract 1 from the exponent, right? So I'm differentiating with respect to x1. So I am going to take 1 from 0.4. So 0.4 minus 0.4 minus 1 gives us minus 0.6. So we have 0.4 x1 to the minus 0.6. So why do I have x2 to the 0.6 here? Oh yes, I do have, yes, I must have this one because that particular variable is L constant. So all I need to do is to drop that x to the power 0.6 to this equation, to the marginal utility here. Now this is for you, Aminatu. You have a problem with this. And for Cody, you also have the same problem with this one. So when you are differentiating the utility function with respect to the variable, remember to drop the variable that you are holding constant. You have to drop it down, okay? It follows the equation. It has to follow the equation. You don't just say 0.4 x1 to the minus 0.6. No, that is not the marginal utility of x1. It is 0.4 x1 to the minus 0.6 x2 to the 0.6. You got it, right? Okay, so that is the marginal utility of good 1. Now, what is the marginal utility of good 2? Now, this time, we are going to hold x1 constant, and then we vary what? x2, right? Again, it is just like eating bread and butter in this case, right? So, all we do here, we take the exponent of x2, and then we multiply by the whole of this one, x1 to the 0.4, and then x2 to the 0.6, right? But remember, here we are holding x1 constant, right? So that particular variable has to drop here. So we have x1 to the 0.4. But remember, we are differentiating the utility with respect to x2, right? So the exponent of x2 is going to change, but the exponent of x1 remains unchanged. You got it? Okay, so it is 0.6 minus 1, which is minus 0.4. So that gives us the marginal utility of good 2. So now we have the marginal utilities. We know the price of good 1, which is what? $1. We know the price of good 2, which is what? $4, right? So it is just easy to find. Now let us use the equimarginal principle here. So what is that equimarginal principle? The marginal utility per dollar spent on good 1 equals to the marginal utility per dollar spent on good 2. So the consumer is in equilibrium when the marginal utility per dollar spent on good 1 is equals to the marginal utility per dollar spent on good 2. Right? So this one should be spent on good 1, not of good 1. The marginal utility per dollar spent on good 1 must be equal to the marginal utility per dollar spent on good 2. So this means that mu x1 over p1 equals to mu x2 over p2, right? Now, mu x1, now using the marginal utilities and prices, this gives us what? Mu x1 is 0.4 1 to the minus 0.6 x2 to the 0.6 divided by 1, and this equals to 0.6 x1 to the 0.4 x2 to the minus 0.4 divided by 4, right? So once we have that, all we do now is what? We multiply both sides by 4. And this gives us 1.6 x1 to the minus 0.6, x2 to the 0.6 equals to 0.6 x1 to the 0.4, x2 to the minus 0.4, right? So, by simple algebraic manipulation here, so what do we do here? We just divide both sides by what? We just cross multiply. We say x1 to the 0.6 minus 0.6 x2 to the 0.6 divided by x1 to the 0.4 x2 to the minus 0.4 equals to 0.6 over 0.1, right? So this, we just divide this 0.6 by 1.6. Now remember, if we have this scenario here, so x1 to the minus 0.6 over x1 to the 0.4. Now, you've done indices before, right? So you know what this one is. A to the x divided by a to the y is a to the x minus y, right? So that's what we're going to do here. Simple. So x1 to the minus 0.6 over x1 to the 0.4 is the same as what? X1 to the minus 0.6 minus 0.4, right? So minus 0.6 minus 0.4 is the same as what? Minus 1. Negative 0.6, negative 0.4 is negative 1, right? So it becomes x to the minus 1. But remember, when we say x to the minus 1 is the same as what? The reciprocal of x1. That is 1 over x1, right? So x to the minus 1 is the same as what? The reciprocal of x1. x1 to the minus 1 means the reciprocal of x1, 1 over x1, right? So we have x2 to the 0.6 divided by x2 to the minus 0.4. Again, we apply the laws of indices here. x2 to the 0.6 minus negative 0.4. And minus negative 0.4 is what? Plus 0.4. So 0.6 plus 0.4, that gives us 1. So x2 to the power 1, right? So x2 to the power 1 multiplied by 1 over x, or x2 to the x1 to the power minus 1, or 1 over x. So that gives us what? x2 over 1, x1. x2 over x1. And 0.6 divided by 1.6 gives us 0.375. So x2 becomes what? 0.375 x1, right? That one is simple. You all got that one, right? Okay, let's move on. Now, plugging for x2 equals to 0.375 x1 into the budget constraint. Now, we are going to plug for x2 into the budget constraint now to obtain the optimal value. So what do we do here? We have x2 equals to 0.375 x1, and then we'll plug this one into the budget constraint. And this becomes what? Because you know the budget constraint is what? X1 plus 4x2 equals to 100, right? Now we are not going to say x2 anymore. We say 0.375 x1 because x2 is equal to 0.375 x1, right? Plug that one in there, and that gives us what? X1 plus 1.5 x1. So you see, 4 times 0.375 becomes 1.5 x1, right? So now, this is so easy, simple, straightforward. So it is equals to 100. So 1 plus 1.5 x1 is what? 2.5 x1 equals to 100. So what is x1 start? X1 start is what? 100 over 2.5, which is what? 40. But we know that x2 is 0.375 x1, right? So what do we do here? We just plug, or we substitute for x1 start into that equation, and that gives us what? x2 start equals to 0.375 x1 start, 0.375 times 40, and that gives us 15. So the optimal choice of the consumer is therefore what? X1 start, X2 start equals to 40 and then 15, right? Simple. This is straightforward. I expect everybody to be able to solve this one. If I bring this in an examination in the finals or maybe the midterm. I want you guys to be able to do this one. This method is so easy. It is simple. It is straightforward. The substitution method. Now, if you are not comfortable with this one, okay, now let's move on to the Lagrangian, the other method. Now let's use the Lagrangian next in this case. Now, if we use the Lagrangian here, we maximize the utility subject to the budget constraint x1 plus 4x2 equals to 100. Now remember here, we are going to use the Lagrangian here, the Lagrangian function here. Now, the Lagrangian equation has the Lagrange multiplier. The Lagrange multiplier is the marginal utility of income. So the marginal utility of income is the Lagrange multiplier. So in this case, I use mu as the Lagrange multiplier. So all I did here was what? I tried to get a composite function. The composite function is the Lagrange function. And that Lagrange function has both the objective function as well as the budget constraint. Now we know the budget constraint is x1 plus 4x2 equals to 100. And so when we introduce the Lagrange there, all we need to do there is to transpose all the variables to the other side of the equation. And that becomes 100 minus x1 plus 4x2, and that equals to 0, right? So it's the same as saying for x1 plus 4x2 equals to 100. So that is the same as what? 100 minus x1 minus 4x2 equals to 0. So I'm going to use that equation to set up my Lagrangian function. Now, as I said earlier, the Lagrangian function has both the utility as well as the budget constraint. It has both the objective function of the consumer as well as the budget constraint. Now remember, this is the science of constraint choice. It is a science of constraint choice. We want to allocate our scarce resources subject to our limited income. So how do we go about doing this? We are going to optimize. So this brings in the concept of constraint optimization. So now I introduce my Lagrange here. What I do now is to differentiate the Lagrange function with respect to x1, x2, and lambda, and mu, and then equate to 0. Right? So I differentiate the Lagrangian with respect to x1, x2, and mu. Now remember, these three variables are what we are going to look for, right? We are going to determine the optimal values for all these ones. So if we differentiate the Lagrangian with respect to x1, we're going to have 0.4 x1 to the minus 0.6, x2 to the 0.6. Remember, we are differentiating with respect to x1. We are holding all the other parameters constant, all the other variables constant. Now, if we hold all the other variables constant here, and then concentrate only on x1, we take the exponent of x1 and multiply by the utility function, right? And that gives us 0.4 x1 to the minus 0.6, because we know 0.4 minus 1 is minus 0.6, and then x2 to the 0.6, and then minus mu. Remember, you have plus mu here times minus x1 is minus mu x1, so minus mu, that is equal to 0. We do the same thing for the function with respect to x2, and then we have this second equation, and then we do the same thing for the Lagrange. Then we get the third equation. When you differentiate this whole function with respect to mu, you only get this one. Remember, there is no mu on the first term, right? So that is why this one collapses. The first term collapses, 0, right? There is no mu there, so you only concentrate on the second term. Good. So we have 3 sets of equations here. So what we do here, we are going to divide the first by the second equation. Do you know why we do that? We do that because we want to eliminate mu. We want to eliminate the Lagrange multiplier. We want to take it off. We want to eliminate that one. Once we have eliminated that one, then we can solve our problem. Now let's proceed. So if we divide equation 1 by equation 2 and then solve, we're going to have this equation. So remember, mu by mu cancel. And then if we rearrange this equation, we're going to have 1.6 x1 to the minus 0.6, x2 to the 0.6 equals to 0.6, x1 to the 0.4, x2 to the minus 0.4. The above equation can be expressed as x1 to the minus 0.6, x2 to the 0.6 over x1 to the 0.4, x2 to the minus 0.4, and this equals to 0.6 over 1.6. Now remember, 0.6 divided by 1.6 is just 0.375, right? So this second term, the term on the left-hand side, if we simplify that one, we're going to have what? X1 to the minus 0.6 minus 0.4, that gives us x1 to the minus 1, right? Which is just 1 over x1. And then x to the 0.6 minus is plus 0.4, that gives us x2 to the 1. And x2 to the 1 divided by x1, that gives us x2 over x1 equals to 0.375. And x2 is what? 0.375 x1, right? So now, this, if you look at this one, it is synonymous to what we obtained before in the substitution method, right? So if you are somebody who is so sophisticated, then you can go with this approach. If you know you are not that sophisticated, you're having some issues, go with that simple approach, the simple substitution approach. That one is just easy. You don't even need to go to Cambridge to know that one. Okay? So you can use that approach to solve all consumer optimizing problems. Now, let's move on. So from equation 3, we have 100 minus x1 minus 4x2 equals to 0, which implies x1 plus 4x2 equals to 100. Now, what do we do with this? All we need to do now is to plug in for x2, which is what, 0.375 x1. Then, in place of x2 there, we just plug it in and then we solve. When we solve, we're going to have x1 plus 4 into 0.375 x1 equals to 100. So if we solve that, we're going to have x1 plus 1.5 x1 equals to 100. x1 plus 1.5 x1 is 2.5 x1 equals to 100. x1 star equals to 100 over 2.5, which is what? 40. x2 is 0.375 x1, right? So we just substitute for x1 star into that. That gives us x2 equals to 0.375 times 40, which is what? 15, right? So what do you notice here? Is this result different from the one we obtained from the substitution method? No, it's the same. So this is just like somebody trying to apply some sophistication, you know? It's the same. So do I need to go with this approach? If I'm able, yes, I will go with it. If I'm not able, no, I'm not forced to do it. So I can go with the simple method, the substitution method, okay? So this is the reason why I try to bring these two. So you can pick which one you want, which one you are comfortable with. If you are not comfortable with this approach, don't use it. If you know you're going to have some glitches on the way when you're solving this problem, using this approach, don't use it. If you know you are well comfortable with it, go ahead, go for it. If you are not comfortable with this one, you are so comfortable with the substitution approach, then go for that substitution approach. It is easy. You get the same answer, the same result. You will not be penalized for using any of the methods. Okay? All right.